And this is Anders Miltner to talk about synthesizing simple symmetric lenses.
Hey. OK, before I actually talk about synthesizing symmetric lenses, I'm going to talk about programming by examples. So programming by examples is a paradigm where users can develop programs by demonstrating the desired behavior of the program on examples. So you don't actually write up the program. You just provide input-output examples. And this has been applied in a variety of domains like spreadsheet transformations, data structures, table transformations, refactoring, and a lot more. These example-directed synthesis engines have a bit of a recipe. First, you have to identify the domain that you want to synthesize within. You design a DSL for that domain. You develop a way to enumerate that DSL, and then you rank the enumerated programs. In this talk, we're going to focus on this last step of ranking the enumerated programs. So there's a few different ways that people do these rankings. Some of the major ones are things like avoid constants, avoid branches, and create short programs. Avoid constants is the one we're going to focus on because this work kind of focuses on string cleaning and string transformations, and avoid constants is pretty useful in that context. So what's the ultimate goal that people try to do with avoiding constants? We claim that the ultimate underlying goal behind avoiding constants is actually retaining information. So how does this relate to synthesizing symmetric lenses? Well, we first tried to synthesize symmetric lenses, and it became really clear that ranking was a huge issue. And performing simpler heuristics didn't really work. So it was super important for us to address this ranking problem. And we found that our solution using information theory provided a nice theoretical basis for prior heuristics that were ad hoc. So in this talk, I'm going to introduce symmetric lenses and talk about problems with synthesizing them. I'm going to propose information theory as a solution, and I'll show you how our evaluation demonstrates that it's actually useful. So first, what are symmetric lenses? I think of them often in the context of synchronizers. So if you have data in two different formats, data 1 and data 2, if I update data 1, I would like data 2 to get an update as well, updated the shared information. And if I update data 2, I would also like the shared information to be updated in data 1. So I'm going to give an extended example, and I'm going to shamelessly keep your attention with a dog. So I have to upload puppy pictures very often. I'm trying to upload it to Instagram to fulfill my dream of being an Instagram influencer. But I also need to upload it to my mom, who wants pictures of my puppy often. So Instagram has two fields that I have to keep track of. I need to keep track of a picture URL as well as a cute status. And my mom needs a picture URL, but she needs a wait because she thinks that I'm underfeeding my dog. So in Instagram, I have the data in a JSON format. So it might have some status like Mondays are the worst, as well as a picture URL. And my mom takes in a CSV format of the URL and the weight in pounds of my dog. So if I update Instagram with a new picture and a new URL, I would like my mom's CSV to also get updated with the same URL. But because we don't have any information about what the weight is, it will just have the sentinel value of unknown, which I can later change to the correct value of 6.8. If my mom asks me for a new picture, I can upload it to her, and then I would like Instagram to get the same picture with the default status of status unset that I can then change to fun in the sun. And notice that when I do that change, there's no change on my mom's format. So in this, I have both shared and unshared information. The shared information is in the context of the URLs, and the unshared information is in the context of either statuses or weights. So we have a language for these symmetric lenses. We write L:(R left right arrow S to denote the fact that L converts between R and S, and in the context of Boomerang, which is what we're synthesizing in, R and S are regular expressions. We have to be able to express shared information, which is the example of URLs. So if I have two URLs and I update one of them, I would like that update to be propagated to the other side. This is done with the identity lens, which takes in a regular expression and creates this synchronizer between that. But then I also need to be able to express unshared information. So for example, weights and statuses, I want it so that if I update the weight, the status remains unchanged. And this is done with the disconnect lens, which takes in also the default values for newly created values. And then lastly, I want to be able to have both shared and unshared information in my synchronizers, so I have to have some structural combinators. So for example, I've got shared URL, unshared statuses, and weights. If I update the status and the weight, I want just the status to be, or just the URL to get updated. And that can be done with the structural combinators, in this case concatenation, but there's other structural combinators to reflect similar things to regular expressions. So let's go into our synthesis algorithm. What we do is we do type-directed synthesis to find a solution. So we take in the two regular expressions describing the two data formats as well as a set of examples. We put them into our synthesizer, and that synthesizer will generate a lens L. That lens is guaranteed to be to map between the two formats, R and S, and it's guaranteed to satisfy the examples. So in our extended example, I would put in a regular expression describing my mom and Instagram's format, as well as an input-output example. So I'm going to briefly go into the actual algorithm, just using pictures and circles. For the purposes of this discussion, let's pretend that we have a ranking. I'll go into the ranking later. And imagine that this pink circle is the space of all lenses. The way we actually do our synthesis is we have two synthesizers, one that proposes subsets of the lenses, and a second one that will quickly find the best ranked lens within that subset. And then it continually proposes new subsets and finds the best lens in that subset until eventually it finds a subset and a lens that is highly ranked enough that it will return it to the user. So that now begs the question, what is the best lens? We claim that the one that we think is the best is the one that is closest to being bijective. Where a function is bijective if for every element of the output there's a unique element of the input that maps to it. So a quintessential bijective function is the one that maps n to n. Something that's not bijective is the one that maps 0 to 0, and for non-zero natural numbers, n to n minus 1. And then there's another one which sends just everything to 0. So bijective is just a Boolean true or false. So the top one is bijective, the bottom two are not bijective. So we want to have a notion of being almost bijective or more bijective. And clearly that second one is, in some sense, more bijective than the bottom one. So we need to be able to create a way of describing this. So we can do this using information theory. So I'm going to give you guys a quick primer on information theory. Information theory and probabilities are tightly related. So the information content of an event and the probability of an event occurring are very related. In particular, they're kind of inverses. So the lower probability a event has of occurring, the higher information content is in it. So for example, if I flip a coin, then there is one bit of information per result. Was it heads or was it tails? But if I roll a weighted die, it's a little bit different. So if I roll on the weighted side, I'll get one bit of information. Did it roll on the weighted side? Whereas if it lands on any of the other sides, it has more information because I need to know, did it land on the weighted side? It didn't. And which of the non-weighted sides did it land on? So that's a way of talking about the individual information content of strings or events. But we can talk about distributions and information content of distributions using entropy. So entropy is a way of talking about the expected information content over the entire distribution. And that's summed by taking the information content of each event or string and weighing it by the probability of that event occurring. So the entropy of a coin flip is 1, but the entropy of a weighted die is higher, it's 1.5. But to talk about information, then, we now know that we need to have probabilities, but we just have regular expressions. So what we do is we make our regular expressions encode both a language as well as a probability distribution over the language. That's done with stochastic regular expressions. Note they're very, very similar to normal regular expressions, but they have these additional probability annotations. These annotations describe how likely it is in a disjunction to take the left or the right branch, and in an iteration to continue iterating. And we can actually calculate purely syntactically the entropy of the stochastic regular expression, provided that the input SRE is unambiguous. Okay, so now we have a way of measuring entropy. With that, we can actually measure how much information is lost using a certain lens. So formally, what is the amount of information that is required to recover a string from T from another string in S when the strings are synchronized by L? So basically, if I'm given a string in L and I know that they're synchronized by the lens L, or if I'm giving a string in S, I know they're synchronized by L, what's the string that I have in T that is synchronized? So if I have the identity lens, it takes no information is lost, because I know exactly, given this string in T, I will have that exact same string in T on the other side. But in a disconnect lens, it's the reverse. I don't have any information, so the amount of information required to recover that string is in expectation, is the entropy of that stochastic regular expression T. And then I have ways of combining it. If I have a concatenation lens, I just kind of sum up the entropy, or the information required on the left and the right portions of the format. And then the cost of a lens is just the sum of the information required to recover the left from the right and the right from the left. So now we have a ranking on lenses. How does it work in practice? Well, we have a benchmark suite of 48 benchmarks from FlashFill, Augeus, and the bidirectional programming literature. FlashFill is existing work that does string transformation, and Augeus is a bidirectional programming utility used by Red Hat for Linux configuration files. The average size of each regular expression in our specifications is around 1600, and the average size of the lens is around 3200. And so these are pretty big benchmarks, and it works pretty well using these heuristics. We're able to synthesize lenses for 42 out of our 48 benchmarks, and also simpler heuristics perform worse. So if we just have kind of no heuristics and just choose the first lens we find, we synthesize none of our 48 benchmarks. And if we use kind of the analog of just avoiding constants, which is counting disconnects, we only synthesize 12 of our 48 benchmarks. Furthermore, our engine is pretty quick. It takes only 26% longer than a bijective synthesizer, which doesn't have any of these complicated heuristics, on benchmarks that bijective synthesizer is able to go. So we don't like 42 of 48, though. We want to get 48 of 48. So we were able to get those final 6 benchmarks using relevance annotations. So relevance annotations are ways of you telling the synthesizer, without just providing more examples, information about the data. So for example, if I know, hey, some piece of data should absolutely be retained, like the URL, I can annotate it with require. And if I know that there's absolutely no use for a data and it can be lost going from one side to the other, like wait, I can annotate it with skip. And we're able to make this work pretty easily in our framework because we address skip by just saying, hey, the information content of the skip is 0, and then there's no incentive to kind of retain the information in the skip, and it just gets disconnected. Requires a little bit more complex in that, but really what all this is saying is just if any of the information that is annotated by require is lost, then the cost of the lens goes up to infinity. So by adding in these two things, we're able to synthesize all 48 of our 48 benchmarks, and they're all able to be synthesized in under 30 seconds. So in summary, we try to find lenses that are as bijective as possible, and information there we go. And information theory can measure the bijectivity of a function. Relevance annotations give us good means of saying whether subcomponents should be synchronized or non-synchronizing. And this is nice because you're able to do this with minor lightweight annotations instead of providing maybe like 5 or 6 more examples. And the semantics of these relevance annotations are clearly defined using our information theoretic framework. And we work pretty well in practice in that we're able to synthesize all our benchmarks in under 30 seconds. Any questions?
Thanks. We'll start with a Slido question. How readable are the generated lenses? Can you tweak them by hand? Are they?
Yeah. So at the start, they're not, but we added in a lot of code to essentially make the lenses a little bit more readable by doing things like factoring out certain subcomponents of the lenses so that, and also pre-printing them, which makes it a lot better. But I would say that it is probably slightly worse than human-written lenses.
Hi, you used information theory as a way of getting a quantitative measure of injectivity. But if you only want a qualitative one, if you only want to ask about whether one thing is more or less injective than another, you don't need the numbers, and there's a notion of kernel of a function. So the kernel of a function f is the pairs x, y, such that f of x equals f of y. So the more of those pairs, the less injective it is. So this induces an ordering on, an injectivity ordering on functions. Did you look at that, and does that work?
Yes, but that kind of hits a limit based on essentially cardinals once they hit up to infinity. So if you have an infinite cardinal of how big your kernel is, then it will be indistinguishable. So unless I'm misunderstanding your...
So you don't get a number out of it, it's just you get an ordering out of it, a partial order on the functions. One function is less than or equal to another function in this ordering if it's so it's more injective if it distinguishes more examples.
Yes, but that still is, I mean, as you said, it's a partial ordering, so there still is incomparable elements. So you can have one that loses the URL and one that loses the status. Which one is better? You don't really know in that context.
Another question from Slido. Have you tried to get regular people, innocent people, as they say, to adopt this? How would you do that? I mean, is there a plugin? Is there?
So it's not yet integrated into the primary Boomerang suite because it's kind of a large change because we're not just adding in synthesis to Boomerang, but we're also adding in full symmetric lenses instead of asymmetric lenses into Boomerang. But hopefully, all consumers of the language Boomerang, which probably exist only in this room, will be able to use our tool.
Yes.
Thank you. I'm curious, how powerful are the relevance annotations just by themselves, maybe with either a very small number of examples or no examples?
So the relevance annotations are really useful for one element of the synthesis, which is should information be lost or retained. But there's another element that almost necessitates you to use at least one example, which is reordering of fields. So it's really useful and great at losing information, but it provides nothing for, if I go from like first name, last name to last name, first name, it doesn't help out at all for that. So I usually need at least one example.
So from Slido, do you use information theory to quantify how many examples are needed for good results?
No.
Yeah.
That would be cool, though.
Audience questions? I'll give another. Does the synthesis process yield insight into the underlying consistency relation of the lens?
I do not know to what you are referring. Talk to me offline.
How do you choose the probability annotations?
Yeah, okay. So we go into this in the paper in more detail. We would like to eventually do some sort of thing where we use data to generate them, but in this context, we just kind of automatically create them from the structure of the regular expressions to try to be fair to different subcomponents.
One more question here. How do you deal with structure? You have lists on both sides. So in particular, how do you choose to align items?
I don't know. Sorry, say that again?
So it's already gone from the Slido.
Oh, no. Okay, well, I guess talk to me offline.
I don't know if I could reproduce it. Any other questions from the audience? Great. Then I thank the speaker one more time. And